It's so good. I'm like, go run it. I dropped it out, bro. So I mean, well, I was thinking, yeah, and I was like, like this is not no. So I dropped my phone. So you know what? So I dropped my phone. Yeah, that was the only one.
So we're going to go ahead and go to Thursday's topic, which is vertical asymptotes, covering infinite limits. And tomorrow we'll do Friday's topic, which is horizontal asymptotes, which I think is pretty easy. But the issue is when all your limit problems get all mixed together, I think it's we got to make sure that we know which category we're in and that we're taking the appropriate steps. And sometimes the issue that I see with students is we tend to want to skip steps, especially if we feel like what's coming up. And then if we skip steps, sometimes we get caught going down the wrong path and it's hard to backtrack and figure out what went wrong. So we're really going to try to emphasize identifying the correct first steps before you start making any conclusions. So let's go to page 15. So we briefly talked about this. We talked about when algebraically we know that there is a vertical asymptote. Whenever we evaluate a limit and we get something like 10 over 0, 8 over 0. But that's all we know. We don't know, we know a limit doesn't exist, but we don't know which subcategory we're in without the graph in front of us. So let me just go back to the beginning here. So infinite limits is limit where the function increase or decrease without bound towards infinity as x approaches c. So that means we're approaching a real number, but the y value is headed towards infinity. So there's 4 different variations. The asymptotes can be both going up, or the branches can be both going up. They could be both going down. One's going up, the other's going down, right? Or one's going down, the other's going up. So they're all, we know that there's 4 options, but we do know that if it's truly an asymptote, our graph is going to kind of move up or down, treat that as a wall, and it's never going to cross it, but it's just going to either go up or down towards that asymptote. If the limit approaches c from either the right or the left, then that c is a vertical asymptote. So the way we find vertical asymptotes is we look at the denominator and we look at the denominator that have no factors that can cancel. So if your denominator doesn't have a matching pair of factors in the numerator, we know that that's a vertical asymptote, because if there was a matching pair, then we know that discontinuity would be a whole discontinuity, that there would be a hole in the graph. So number 1, it says find all vertical asymptotes of our function. So let's go ahead and factor everything out, and whatever remains in the denominator is that does not cancel out is your vertical asymptote. Okay, to try factoring, try to identify those holes or the asymptote, vertical asymptote. So if I factor my numerator, I know with factoring the denominator, if I factor x minus 2x plus 2, x minus 2 cancels out. We know that that factor tells us the location of the hole. The vertical asymptote is coming from that x plus 2. So if I set that equal to 0, solve for x, we know there's a vertical asymptote at x equals -2. Okay, so now let's look at some of these problems here. there's all these steps. I'm just going to jump directly into well, trying this problem from what we know, and then when we get stuck, we can talk about the next step. So it says limit as find the limit as x approaches 2 of our function x plus 1 over x minus 2. So let's go ahead and do that. Okay, this is algebraic limit. We're approaching a real number. What's our first step? Yeah, direct substitution. We get 3 over 0. What does that tell us? That there's a what there? Their vertical asymptote. Therefore, the limit. What do we know about our limit if there's a vertical asymptote? Does not exist, right? So that's our answer. But we don't know what subcategory we're dealing with, right? We don't know if the branches are both headed up or they're both going down. If they are both going up or going down, we can create a subcategory, but we don't know. We just know there's vertical asymptote. We don't know how the graph is looking around that asymptote, especially if we don't have a graph in front of us, and we're not going to really spend the time to find all these ordered pairs and sketch the graph. Okay, so this is we're going to talk about how we can subcategorize it without the use of a calculator. Okay, which means that we have to look at both the left and the right side independently. Okay, so let's do that. Limit as x approaches 2, the left side of 2. So here's what I want us to make sure that we always do as our first step, because after I show you this method, you're going to want to be tempted to just jump into this method or assume that it's always this method, but it's not always that way. So first thing we always do is, even if we think we know what's going on, we always want to do direct substitution. Okay, so never skip that first step. All right, so plug 2 in, we still get what? 0 over 0, okay? We know there's a vertical asymptote. We know limit doesn't exist, but this problem is not asking about the full limit. It's only asking for the limit coming from where? From the left, which means that there's only 2 options. It's either going to be what? Positive infinity or infinity, right? We know that there's a vertical asymptote at x equals 2, but we just don't know which direction it's headed. Is it going up or is it going down? And we're going to decide this using this algebraic method that we're going to talk about, or numeric method we're going to talk about. Okay. So now that you know there's vertical asymptote, and now that we know that we're only deciding between 2 options, we're going to test a decimal value. We're going to test a number that is to the left of 2. So give me a number that is close to 2 on the left side of 2. 1, right? But we're going to get even closer than that. We're going to just be 1/10 away from 2 so that if there's any issues, we can catch it. So we're going to try to be a bit more accurate than just 1, but that's the idea, that we do want to pick a number to the left of 2, but a little bit closer than 1. So we're going to test x equals 1.9. Right. So if we plug 1.9 in for this, whatever sign we get is going to kind of give us a good idea where the graph is headed, because we're only down to 2 options. So we're going to test a number that is coming from where we are headed. So now we're going to insert 1.9 in for all the x's. Okay, this feels like it's a very tedious thing, but it's not that bad. I'll show you why. We don't have to worry about what this value is equal to. I just want to know what the signs of the numerator and denominators are, so I can conclude between these 2 options. Okay, so don't feel like, oh, I have to divide by a fraction. I got to do all this calculation. You really don't. You just have to tell me whether it's positive or negative. So the numerator is what? Positive or negative? Positive, right? Denominator 1.9 minus 2 is going to be a negative value. Positive over negative is negative, so therefore negative infinity. So we know that getting closer to this asymptote, we know the graph's going to look something like that. And that's going to be our answer if the problem is asking you for a one-sided limit. If it's asking for a one-sided limit, We always want to make sure that there is a vertical asymptote. That's why we always do this first step. And then once we confirm it, we don't want to say does not exist. Even though the full limit doesn't exist, we know just from the left side, the behavior is headed down towards negative infinity. Let's do it. Let's find the limit from the right side of 2. Okay, let's go through our first few steps. Direct substitution first. We still get what? 3 over 0. This tells us, oh, there's a vertical asymptote. If we're approaching a vertical asymptote, we can only do 2 things, right? It's either going to go up like this or it's going to go down. One of these 2 options. We don't know which one is which, or we don't know which one this graph is looking like. So now that we're down to 2 options, what can we test? 2.1, yeah, just within the 10th. And don't worry about trying to get a numeric answer. All we care about is what are the signs once we plug in. All right, numerator is positive, denominator is, and so therefore positive. Okay, so the graph looks something like this. So the left is negative infinity, the right is positive infinity. We know the graph is going to have opposite directions in terms of its asymptote. So going back to this original problem, even though the full limit doesn't exist, are we able to subcategorize? No, right? The directions of the arrows are not the same behavior, so therefore our full limit will still remain doesn't exist. Now, even if we could subcategorize, it is still under the umbrella of does not exist, but we're not able to give a visual description beyond does not exist. Okay, next page. Now, here's the danger that students experience is that from now on, whenever you see a one-sided limit, you may instantly want to think that that must be a decimal, that must be a vertical asymptote, but we don't know. Okay, so sometimes one-sided limit can sometimes be disguised as a vertical asymptote, which is not always true. Okay, sometimes that is just a distraction. Sometimes one-sided limit is just it's a normal limit problem. There may be a hole or there may be a real number. And if the limit exists, the one-sided limit is always going to fall in line. So we always want to just assume that we don't see that one-sided limit. We're always going to do direct substitution. And if we realize that there's a vertical asymptote, then we can look back at the problem and realize, okay, there's a vertical asymptote, but the limit is only asking from the left or from the right. Now I can look at decimals. So we always want to do direct substitution first, because sometimes the one-sided limit is just the same as a limit. So number 3, first steps first. What do we do? Good, direct substitution. Ignore that plus minus sign. Pretend like you don't even see it. Let's just see even if the true limit exists, because if it does, then the one-sided limit will be the same as that limit. Okay. It's only going to give us a different step process if we realize there's a vertical asymptote, but we don't know which category we're in, so we always have to plug in. Okay, so what do we get in the numerator? 0, and denominator we get -7. Now, what does that tell us? That is a number. That's a real number, right? That is 0. That's our answer. So the full limit is 0, which means that the left and the right will always be in agreement. We don't do anything separate with that one-sided limit. That is just a distraction to see if we're going to fall for the fact that that there may be a vertical asymptote, but we know there isn't, right? Direct substitution tells us there's no vertical asymptote. The limit exists. There's no need to do anything different there. All right, number 4. First steps. Direct substitution, right? Don't look at this and say, oh, I gotta do a decimal because I see a left. We don't know. We don't know what's going on yet. Okay. What does this tell us? There's a hole, which means that the limit does exist. The one-side limit is there to distract us. We're just gonna do a limit problem like we did on the quiz. Right? This is no different. Which means we got a factor, right? We're looking for a hole. All right, what do we see? Anything cancel out? X's. Now we can do what? What's our next step? Direct substitution, right? So 0 in for x, 5 minus 0 over 0 minus 1. That's just -5. So we haven't done anything different than what we were able to do on the quiz. It's just that we have to look at that notation and not be distracted by it. Okay, number 5. First steps first. Direct substitution. Numerator, we get 5. Denominator, we get 0. So we know the full limit is what? Yeah, full limit doesn't exist. But can we stop here? Can we just say it does not exist? Now we realize, okay, limit doesn't exist. There's a vertical asymptote, but it's not asking for the full limit. It's asking for how is the graph looking as we approach that vertical asymptote. So now we can do what? Now we can use decimals, right? Now we know that if we're approaching -2 from the left of -2, the graph will look like this, or it will look like this. Now we're trying to subcategorize, or sorry, we're trying to decide the behavior of the graph towards that asymptote. Okay. We want to pick a decimal. We want to pick a number to the left of -2, a tenth away. Let me show you on the number line here that negative is a little bit opposite here. So let's say this is -2, this is -1, this is -3. I want a number that is right here. What is slightly to the left of -2? Yeah, -2.1. So it's a little bit opposite. If you feel like you want to draw a number line, just convince yourself that you're picking the correct decimal. Because if this was +2, then you would say 1.9, but on the number line for negative, everything is opposite. So to the left of -2 is -2.1. Okay, so we'll test with -2.1. Numerator. Denominator. It looks messy. It looks like this is too difficult to do without a calculator, but it's not that bad, right? We just care about the signs and we don't care about what that value is. So numerator is what? Positive or negative? Yeah, the negative 2.1 is inside the square. So that square is going to force it positive. So numerator is positive. Denominator is therefore negativity. The movement towards the asymptote from the left side is headed down to negativity. It's not asking for the full limit. It's only asking for the one-sided limit. Okay. Let's look at number 6. First steps first. So 3 times 5 squared, 3 times 25, 75 minus 174 over 0. What does that tell us? Therefore, limit does not exist. Okay. Technically, we should be also looking left and right to see if the arrows are matching up. If they're matching up, we can subcategorize, but but this is acceptable. But yeah, so right now we just stop and say the full limit doesn't exist. Subcategorizing would have us looking at the left and right. We'll save that for later, but I want to get through the rest of this. But we know that the full limit doesn't exist, but we don't have a subcategory unless we look at the left and the right separately. Okay, try 7. Okay, what do we get after direct substitution? 0, 0, which means that there's a what? There's a hole. The limit exists. We don't care about that one-side limit. That limit notation is there to distract us. Just pretend like it's just x approaching 3. You know there's going to be a real number answer. The one-side limit, it'll be the same as that. So no decimals, right? We only do decimals if we realize there's a vertical asymptote. If it's a whole or a real number, we don't do anything different. So we know we got a factor, and after factoring, we want to find an x plus 3 in the numerator to cancel that out. Okay, try 8. Are we okay with 7? All right, number 8, first steps first. What do we do first? Yep, direct substitution. 2 times 4 squared. 32 minus 1 is 30. Denominator, we get 0. What does that tell us? That there's a what? Vertical asymptote. We know the full limit doesn't exist, but is this asking for the full limit? No, it's only asking from the left side. So if we're approaching -4 from the right side, there's only 2 options, right? It's either going to go up or it's going to go down. Now that we're down to 2 options here and we're deciding between these 2 options, now we can do what? Test decimals, right? So here's -4, here's -3. What's slightly to the right of -4? -3.9. So a couple of things we have to be convinced of a couple of things before we jump into decimals. Sometimes, again, one-side limits may just mean find the full limit. Okay, numerator, we get what? Positive. Denominator, now -3.9 is slightly less than 4, right? You know 4 squared is 16, So 3.9 squared is going to be less than 16, like maybe 15-ish or right, 15 point something. So therefore denominator will be what? Negative. So positive or negative is negative infinity. So that's our answer. It's only asking for the one side limit. It's not asking for a full limit. If you say it doesn't exist, that is not correct, right? Because if we're just talking about the left or from the right, we can give an answer for that. All right, try number 9. Okay, so it's so important that we take our direct substitution first step because the problem can sometimes disguise itself in ways that we're not able to catch. So if we do direct substitution, we instantly know what category we're in. Are we dealing with a real number where we can just stop? Or dealing with a whole where we got to go through our processes of factoring and reducing? Or are we dealing with a vertical asymptote where the limit either doesn't exist or the one-side limit tells us to play with decimals? Okay, what do we get? Direct substitution first, what do we get? Numerator, we got -1. Denominator, we get 4. That's a real number, right? We don't do anything with decimals. We have a limit. If the limit exists, the one-side limit will also be the same as the real limit. Okay, number 10. Direct substitution for number 10, we get 0/0. We know the one-side limit doesn't play a role at all. It is just going to be a normal limit problem where we have to factor, cancel, reduce. GCF first. Once your 2 is out, then you can factor the rest. You're looking for an x minus 3 to show up in the numerator so you can reduce. Okay, let's go to page 22. Okay, let's see how we do with these problems here. Remember, always show your first steps. I'm looking for that on the test as well. Um, Even if you get to the right conclusion, but if I don't see that first step, you may lose a point. So make sure you always do the right substitution. That is gonna work, that's gonna go towards your to earn full credit. All right, so try this. I'll work alongside you guys and show the answers as well, but go ahead and try. Any questions? Okay, let's end with one problem. I want us to review, just do another practice continuity condition. So page 19. We'll end with number 7. So page 19, number 7. Direction says, use continuity condition to show that the function is discontinuous at a point and state the reason for discontinuity, and then determine whether it's removable or non-removable. We're just going to go through our conditions. Find the point, find the limit, determine if there's a need for one-sided limits. Make sure you're writing out your full reasoning here. We do have a need for one-sided limit because we see less than, greater than. We have different graphs on either side of 3. The fact that one-sided limits are not in agreement. We have jump discontinuity. One side heads to 5/2, the other side heads to 2. The arrows are not pointing in the same direction. So we want to give that full step of showing that the reason why the limit doesn't exist because the one-sided limits are not in agreement. Make sure you put f of x when you are referencing your function. Therefore, the full limit doesn't exist. We can stop and we know it must be a non-removable discontinuity at x equals 3. Okay, so check your calendars for homework. Tomorrow we have one more topic. We're a day ahead, and then we can maybe even begin review tomorrow, but we'll definitely have Friday as our first full day to review. All right, come get your phones.